about putting charges across plates. All right, let's see. Here we go. So to begin with, scientists use these things called schematics. Schematics are our way of describing complex pieces of equipment or situations with easy to use symbols. So here we go. Here's a schematic. This is a battery. So we use this symbol for a battery. It's got a long, so let's see. Short line, short line, long line. And then a line coming off of it. It goes to the rest of the circuit. So this is symbol for the battery. The long line is positive. The short line is negative. The way I remember this, long line takes a lot more ink to draw, and so does the plus sign. The minus sign takes less ink, so that's a shorter line over there. Long line, positive, short line, negative. You can orient the battery in any position you want to, but it's short, long, short, long. Sometimes I see it's really 2 lines. Sometimes I see them like 11 or 10 lines. I don't know why. They do it differently like that. But for us, we're just going to do 4 lines, short, long, short, long. So that's a battery. This is a wire coming off the battery. And then for us, what we're doing, we're going to do this with metal plates. So we'll put a metal plate here and a metal plate there. So those are going to be the metal plates. And the metal plates are not a standard symbol. It just fits for what we're doing. So this is our part of the schematic. In a couple of chapters, we do more with circuits. We're going to do more with batteries and other components as well. So this is what it looks like for our metal plates right now. And as we get into other components, we'll see how this fits into the big scheme of things. So what's going to happen here is that the plate on the right is connected to the positive side of the battery. So that's going to make this positive. So there's going to be an absence of electrons over here. And on the other side, it's connected to the negative side. So that's going to make this side negative. Now this will have an electric field going between. The electric field is always the path of a positive particle. So if I dropped a positive particle here, the question might be, which way would it go? Well, it's going to be repelled from the same sign and attracted to the opposite sign. So it's going to be repelled from the positive. It's going to be attracted to the negative. Now this is the direction of the E field. The E field is defined as the direction a positive particle would travel. So it would look something like this, with lines evenly spaced going across that. So that's important. The E field is the path a positive particle would travel. So let's see if I can write this. E field, is the path a positive particle or charge, whatever you call it, would travel. So that's our definition for the E field and how to figure out its directions right there. All right, now let's talk about a new unit of energy. Our new unit of energy that we're going to use is really, really small, and it was devised to make the math easy. So we know about a joule, but we probably don't know about something called an EV. An EV. So an EV is an electron volt. Electron, capital V-O-L-T. So electron volt, that's our new unit of energy. And as it turns out, 1 EV is equal to 1.6 times 10 to the negative 19 joules. And in fact, this number right here, I rounded it, it's actually the same charge that you would put on an electron. So 1.602 and some other decimals times 10 to the negative 19. We'll just use 1.6, so no, 1.6 times 10 to the negative 19 joules. So an EV, negative 19 joules, that's like 16 millionths of a joule. It's really, really small, but so is the charge of an electron. It's done like this on purpose. All right, so what we know so far is that if I have 2 metal plates, 1, 2, and they're connected to a battery. So let's see, I'm going to do long, short this time. So I'll turn my battery around, connect the other metal plate. And let's say I have a charge in here. And this charge has a value equal to, let's say, 4 protons. So that's the charge. And there's going to be a little hole in this plate that I can't draw. It's going to go through that little hole, and it's going to enter this region between the 2 plates. So I know a couple of things. I know the electric field is going to go from positive to negative, because remember, electric field is the path a positive particle would take. It would be repelled from the positive side and attracted to the negative. So there's our E field. I can also calculate the work that's done in this. So let's say this battery is a 10 volt, sorry, 10 volt battery. And I know that the work that's done is equal to Q times V. So that means that the work that's done is equal to 4 times the charge of a proton. So I'm gonna write as a P for the moment, times the voltage between the two plates that it goes across, the potential difference. And that potential difference is 10 volts. So that means that the work is equal to 4. And then I'll look at Google, I'll look at a sheet, and I figure out the charge of a proton is 1.6 times 10 to the negative 19 coulombs times 10 volts. So that's going to be the work of our charge going across. Let's see, 1.2, 6.4. So the work is going to be equal to 6.4 times 10 to the negative 18 joules. Now here's the cool thing about electron volts. If I have this charge going across, it's got equal to 4 protons. That means it's 4 times the charge of the magnitude of an electron, because an electron is 1.6 times 10 to the negative 19. So if it's 4 times the charge of a magnitude of an electron times 10 volts, then the work is equal to, get this, 4 charges times the size of an electron times the volts. Sorry, I don't have units on that. So that would be 40 EVs. So that's why we have EVs. EVs are so easy to work with, as opposed to joules using the 1.6 times to the negative 19. Our quantities are so small that working with energy units of EVs makes things a lot easier. Okay, so let's take a look at another kind of problem. Let's expand this out a little bit. Here's my metal plate. Okay, here's my charge. Let's do short, long this time. So I'll turn my battery around again. Okay, here's my other metal plate. And let's say I have a charge equal to, I don't know, let's make it easy, 10 electrons. So whatever this particle is, it has a net charge equal to 10 electrons. It's moving towards this way. And it's moving towards this with 100 EVs of energy. And what I want to figure out is, let's say, how much energy in EVs, sorry, it's hard to write like this, EVs, does it have after crossing the plates? Crossing, it's hard to write like this. So I'm not looking at my hands. Some people have skills. So that's what I want to figure out. All right, so it enters this region with 100 EVs. It's 10 EVs. Let's say this is a crazy 5-volt battery. So what I need to do first is figure out if this particle with a charge of 10 electrons is going to speed up or slow down. So if it's going to lose energy or gain energy. Okay, let's go back to my battery. Long side is positive. So that's positive and that's negative. So if I look at this, think about it. This plate over here is going to be all positives. And this plate is all negatives. And I know that because the positive side, positive plate, is connected to the positive side of the battery. That makes it positive. The negative side is connected to the negative side of the battery. So this is an electron with a negative charge. This is a positive plate, so it's going to be attracted. It's going to speed up as it goes across. So it's going to gain energy because it's speeding up. So it's going to gain energy as it goes across the plates. Great. Now the question is, how much is it going to gain as it goes across the plates? Well, it's going to gain 10 times 5, 10 charges equal to the size of an electron, times 5 volts. So it's actually going to gain 10 times 5 equals 50 EVs of energy. So it's going to gain 50 EVs. So it starts with 100, it gains 50. On the other side, it's going to have 150 EVs of energy. And if I needed to, I could convert that over into joules. 150 EVs times my conversion factor. 1.6 times 10 to the negative 19 joules per EV. And that'll be the answer in joules. And I don't have a calculator handy to do that. Okay, let's look at one other problem. Same kind of thing, just a little more practice. So 2 plates, distance apart doesn't matter, you notice that. And I'll connect them to a battery. I'll do long, short, long, short. So let's see, and I'll have a charge equal to 2, let's say positron. It's just E or E plus. So that's all I have going across here. And let's say that this is a, easy math, 10-volt battery. And that's going to be entering between the 2 plates. So right here, it's going to have 50 EVs of energy. All right. So first, let's see if it gain, and I want to do the same question. I'll figure out what it has on the other side. So does it gain or lose energy? Well, let's look at my charges. This is the negative side of the battery. So if that's the negative side of the battery, that makes this negative because it's connected to the negative side. Positive side of the battery, that's positive, positive, positive. If it's a positron, it's an electron with a positive charge. So it would be attracted to the opposite side. So if it's attracted over here, it's going to gain again. So it's going to gain energy. And how much is it going to gain? Well, it's going to gain 2 times 10 volts. So that's 2, oops. That's going to be 2 times 10 volts. So it's going to gain 20 EVs. So it's going to gain 20 EVs. So it starts with 50. I gain 20. So that means I'm going to have 70 EVs by the time I get to the plate on the other side. Now, if it ever loses, it'll go towards the same sign on the opposite side. So if I had switched this battery around, let's see, minus short, long, short, long. There's my plates. So here's the positive side, here's the negative side. So that's the positive side, that's the negative side. My little charge here, as it goes across, that's positive, and this is a positive plate. So in this case, it would lose energy. So I just take what I started and I subtract whatever the difference is of energy. Let's say it's the same problem, just with a reverse battery. So 50 EVs, let's see, this is 10 volts. So it's going to lose 20 EVs. So that would be 50, lose 20. That's going to leave 30 EVs on the opposite side. And if you don't have enough energy to make it to the other plate, it turns around and goes back. It doesn't make it to the other